Hello! In this video we will talk about the energy associated with rotations. Just as kinetic energy is associated with mass and linear velocity, according to this formula, there is also kinetic energy when an object rotates. The kinetic energy of a rotating object is given by this formula. This is the formula we should have expected, since rotational inertia substitutes in for mass, and angular velocity substitutes in for velocity. In order for this to have the correct units, the angular velocity in this formula must be in radians per second, not in degrees per second. Also, just like the direction of the velocity doesn't matter for linear kinetic energy, just its magnitude, the same is true for angular kinetic energy. Only the magnitude of the angular velocity matters. It is entirely possible for an object to have both a linear and rotational motion at the same time. For instance, imagine a baseball flying through the air. It has some linear velocity, but it also spins. In that case, its kinetic energy is a combination of both its linear and angular motion. So we can write this equation, which says that its kinetic energy is the sum of its linear kinetic plus its angular kinetic. For linear motion, we have this formula, which says that the work done on an object is the force times the distance over which that force acts. At least this is true when the force is constant over that distance. We also said that this work done by a force equals the change in kinetic energy of the object. Well, it turns out that a torque can also do work on an object, thereby changing its kinetic energy. That work is given by this formula, which says that the work equals the torque times the change in angular position over which the torque acts. Again, this formula only really works if the torque is constant over that change in angle. This formula also requires that we measure the change in angle in radians and not degrees. Let's do an example for this. Let's say we have a motor that tries to make a fan spin, and it outputs a constant torque of value tau, which is this curvy T thing. The fan has a rotational inertia of I. At first, the fan is not spinning at all. After 2 full revolutions, what will the angular speed of the fan be? Well, we know that tau times the change in angular position equals the work, which equals the change in kinetic energy. The change in angular position is 2 full revolutions, which means going around the circle twice. In radians, which is what we need to work in, going around the circle once is 2 pi, so 2 full revolutions will be 4 pi. So let's just update our equation here. Now, the change in kinetic energy is the final kinetic energy minus the initial kinetic energy. Since initially the fan is not moving, the initial kinetic energy is 0. So the change in kinetic is 1/2 times I times omega final squared, where omega final is the angular speed after the 2 full revolutions. Now we can put these two equations together since they both equal change in kinetic energy. So now we just need to solve for omega final since that is the final angular speed, which is what we wanted to know. So we just multiply both sides by 2, and then we divide both sides by I, then we take the square root of both sides, and great, we have our answer. Let's summarize. The kinetic energy of a rotating object is given by this formula. Keep in mind that angular velocity should be in radians per second. We also learned that the work done by a torque is given by this formula, where the change in angle is in radians. And that's it for this video.